It is incumbent upon every visionary and every practitioner of technology to ensure that future generations have a home. Humans are not the problem. Hubris is, greed is, complacency is. Now is the time to leverage what we know for the benefit of posterity.
Welcome to the Friends of Space Resources podcast, a place to explore space resource exploration and utilization. What is it? Why it matters? And why it's so vital to the future of space investigation. Each week here, we'll meet with a technical expert in the field of space resources to better understand and gain deeper insight into their field of study. Welcome your host, Valerie Eastman.
Hey. Hello, and welcome to this episode of Friends of Space Resources. I'm your host, Caleb Eastman. I'm standing in for Valerie Eastman. Each week on our program, we host an expert in either space resources or related fields. Sometimes our guests are not directly working in space resources, but specialize in a relevant field here on Earth. In order for space resources to become a reality, we have to engage experts from a wide variety of disciplines. I'm excited because my guest today, actually, Dr. George Sowers, is an expert in space resources and is directly working in the field. And so we'll be talking to him. What I'd like to do first is, welcome you to the show, Dr. Sowers, and also ask if you can give, anyone who's not familiar with you a little bit about your background.
Yeah, thanks. Thanks, Caleb. I actually come to space resources fairly recently. Most of my career was spent in big aerospace industry. I started after getting my undergraduate degree at Georgia Tech and my PhD at CU Boulder in physics. I spent 30 years in the aerospace industry, first with Martin Marietta, then became Lockheed Martin, and then Lockheed Martin spun out a company called United Launch Alliance, where I spent 10 years. I was the first vice president of business development and advanced programs. My career was pretty interesting, almost entirely in the rocket business. While I was at Lockheed, I was the chief system engineer for the development of the Atlas V rocket, and then the director of mission integration. At ULA, I was vice president of business development and advanced programs. I helped establish the human spaceflight division there, and I was the first vice president of the human spaceflight division at United Launch Alliance that human rated the Atlas for launch of the Boeing Starliner capsule that still hasn't had its first human launch. By the way, we keep waiting for that. The last few years at United Launch Alliance, I was the chief scientist and vice president of advanced programs. And I got interested in space resources because we were creating a new upper stage at the time called ACES. Now it's been renamed to Centaur 5 that could be refueled in space using liquid oxygen, liquid hydrogen propellants. And so that got us interested in finding sources of propellant in space, because if you can refuel from propellant sourced in space, you can essentially break what's known as the tyranny of the rocket equation, which is that exponential increase in propellant required to do a certain amount of delta V, which I fought all my career in the rocket business. In 2016, I came to Golden to the Space Resources Roundtable, and I had met Angel Abud-Madrid, who's the director of the Center for Space Resources at Colorado School of Mines. Anyway, I came to the Space Resources Roundtable, made a presentation about refueling, and offered that audience of space mining professionals to buy propellant in space. And I actually gave them a price that I would be willing to pay that would close the business case for United Launch Alliance to refuel in space. And I retired a year later from United Launch Alliance, and Angel approached me, telling me about a new graduate program in space resources that they were starting up, and asked if I would like to come join the faculty. And at that point, it was a no-brainer. So from 2017 to now, I've been at the School of Mines supporting this graduate program in space resources. My current research interest is still in that propellant side, but looking at how we actually can mine water ice on the moon and convert that into liquid oxygen, liquid hydrogen propellants.
So that's awesome. So I don't know that, I remember seeing the news that ULA had set the price, for purchase of water on the moon, cost per liter. And it was crazy. It was crazy when I actually got to meet the guy who did that. So, speaking of the extraction, sort of the extraction of water ice on the moon, you're one of the leads on the lunar thermal mine concept for doing so. I'm curious, sort of, since you wrote the abstract, it might have been a year or two ago, that sort of has made the rounds. I'm curious, sort of, how that extraction method has evolved. Is there anything sort of updates in your thinking, or any further research that you've done that's given you some further insight into it?
Yeah, I mean, I think we can probably start out by talking a little bit about what it is. So current scientific thinking is that there is water ice in permanently shadowed regions near the poles of the moon. No one really knows the exact state of this water ice. And there are a number of different theories for how it got there. The most, I think, plausible and accepted theories are that during the early bombardment period in the solar system, comets and or asteroids that had water content hit the moon. That water was vaporized. Over time, it migrates, and if it gets into one of these permanently shadowed regions that are super cold, then it gets stuck. So it traps the ice. So with that model, all the ice starts out on the surface. It gets churned into the surface by continuous meteorite and micrometeorite impacts, process called gardening. But we've done some analysis, and a recent new addition to our faculty at Mines, Kevin Cannon, has also done some analysis that indicates that most of the ice is probably still within the first meter. So if it's very close to the surface, then maybe we don't need to excavate. Maybe we don't need to dig up the soil and cook it to get the ice out. Maybe all we have to do is heat it from the surface. So that's the idea behind thermal mining, is that we apply heat directly to the surface of the moon and sublimate the ice. So it's very cold. It's in a hard vacuum, so the ice will go straight from solid form to vapor form. And so now the trick is, how do we get the energy in there to provide heat? Number one. And number two, how do we collect that vapor? And then so we can process it into propellant. So that's the idea behind thermal mining. There are a number of ways to get energy down into these permanently shadowed regions. The most efficient, if we can make it work, is just to reflect sunlight. So if you can have big mirrors called heliostats that can, receive sunlight up, say, on the crater rims above these cold bottoms, shine it down into the bottoms, and then it can be redirected directly to the surface. That's the most efficient way, because reflection can have efficiencies up 95% or greater. In contrast, if you receive sunlight on photovoltaics at the surface and then power beam it down, those end-to-end efficiencies are probably, no more than maybe 15%, if you at the very best. So to keep the cost down, we started looking at reflected sunlight, and the idea is sunlight comes down, impinges on a second mirror that's above the surface, and so it's directed straight down onto the lunar surface. To collect the vapor, we put a dome-like tent structure over the surface that we're heating. The top of that dome is transparent to allow the light to go through, but then it's IR reflective in the infrared. So as we heat up the surface, what we want to do is trap the heat inside that dome. So that dome is kind of acting like a greenhouse. And the idea is that we're heating the surface and then releasing the vapor. Attached to this dome-like tent are big metallic tanks that are connected by a large passage through the tent. So once the vapor is released, it migrates through that passage into the metallic tank where it refreezes, because those tanks are out in the cold of the permanently shadowed region. And then once the tanks get full, you drag them off to the processing facility and turn the ice into liquid oxygen, liquid hydrogen through electrolysis, which is a kind of a standard process that's used in industrial scale on Earth. So that's the idea. The idea was conceived in late 27. It was conceived earlier than that, but we did some work on it in late 2017 at Mines with a contract that we had from United Launch Alliance, which is a contract actually put in place before I left. And then, we did some low-level work on it. I wrote a NIAC proposal, that's the NASA Innovative Advanced Concepts proposal, that was accepted. And so I think it was turned on, we started working on that in June of 2019, and it's about a 9-month contract, and we finished that work up earlier in this calendar year. And I think the final report was written in March. With that NIAC grant money, we were able to actually do some experimental work in our cryogenic vacuum chambers at Mines, where we created small samples of icy regolith, mixed ice grains in with lunar soil simulants, and then shined a lamp on the surface and measured how much ice we were able to remove. And we were able to prove with those tests that it does work. And it works, as you can imagine, it works really well for ice that's just directly on the surface. All that ice gets removed very quickly. It takes longer for the heat to penetrate into the lunar soils, even in the presence of ice. And but we were still able to show that, we can get down, centimeters worth of depth. Our sample was too small to show how deep we could really go. But we definitely proved the concept that direct surface heating can release ice. Over the summer, with some of my own money, and with an apparatus that we purchased at the tail end of the NIAC grant, a much bigger apparatus, we were able to show that we get even further penetration. So it's all still looks very promising that this could happen. Right now things are not moving much. Number one, I don't have any money to pursue it at the moment, other than just my own time thinking about things. And number two, the student I had that was doing the testing has moved on to other projects. But we're still hopeful, and I've got a proposal in NASA's hands right now through the Luster program that if that gets awarded, we can take this idea much further.
So that's So if anyone's NASA is watching, um, at some point, I imagine that you reach a point of dehydration in a particular area with the dome, and in which case you have to move the dome. I'm curious, is is the idea to have sort of a multi-role rover or something to just kind of drag the domes around, or and then I guess I'm assuming we'll need to repoint the heliostat at that point, et cetera. So you kind of have like a coordinated system that you kind of have to sort of be doing all these types of tasks. That I'm imagining that's kind of what you're thinking.
Yeah, no, as part of the NIAC study, we did look into those logistics, and we came up with a design concept for the tent itself, and essentially the tent has some legs that are retracted when it's snug against the surface for ice extraction, and then those legs can be jacked up, if you will, and it lifts the tent up. At the bottom of the legs are kind of like sort of a disc kind of a thing, a hemispherical shaped disc that allows it to kind of slide across the surface. So the idea is that we're going to drag it. We're trying to keep everything very simple. And then the ice collection tanks are mounted on top of rovers that we called ice haulers. And in the architecture that we've developed, there's, I think, two of those. There are three of those in the architecture, and the idea is that on one side of it they have the opening for the ice collection. On the other side they have a trailer hitch, so they hook on to pick up points above those skids, and then they drag, two of them in concert, drag the tent to the next location, which we would assume is just right adjacent to it. So you're not dragging it very far. You're just sort of dragging it 1/10 diameter. The notional diameter of the tent's about 30 meters. So it's a big structure, deployable structure. And then you set it back down. So yeah, there's 3 ice haulers in the architecture that do that sort of that logistics.
And do they take it all the way up to the crater rim? Basically, do they have like a path that they take it, or is they drop it off somewhere? And
no, the idea, the craters that appear to have the highest concentrations of ice, which is where you would go from a mining standpoint. You want to go to the mother lode, right?
Right.
Those craters are deep and inaccessible from the rims. Okay. So the idea is that the whole operation is permanently at the bottom, and is delivered to the bottom by the landers. So the whole thing is set up down there. It never comes out. There's a landing pad, in the bigger picture architecture, there's a landing and launch pad. So, you have tanker vehicles that are landing down there, filling up with propellant, and then delivering that propellant to wherever customers are to buy it. From a ULA perspective, and this gets into the broader architecture, we imagine that you would have, say, a distribution node at like EML1, Moon Lagrange point number 1, that would store propellant for short amounts of time. And then you would have tanker vehicles that would distribute that propellant to missions. For example, a mission going from Earth to the Lunar Gateway habitat would be refueled en route from propellant delivered from this logistics hub at EML1 that ultimately came from the poles of the moon. And if you can do that, then the cost to get from Earth to the gateway can be reduced by a factor of 2. That's it. That's the motivation, is that back to what I said about breaking the tyranny of the rocket equation, that refueling is a game changer. And so ultimately what we want is to mine, get the propellant from the moon and eventually asteroids. And then it becomes a commodity that can be delivered throughout cislunar space to dramatically lower the cost of transportation.
Well, this is really fast. So in this case, the only thing that's sort of quote unquote out of the crater is the cryostat or the heliostat. Sorry.
Yeah. So the heliostats are, notionally, in the architecture we had 3 of them.
Mhm.
Trying to provide as much coverage as we can throughout the lunar day and lunar year.
Mhm.
So as the sun, migrates on the horizon around, 360 around the moon, then we want to be able to collect that sunlight and direct it down. So there's, notionally three locations for heliostats on the crater rim, and then all the rest of the hardware's in the crater bottom.
I'm sorry if this is too far into the weeds, but I'm curious on the since the rovers are fairly mobile, do you have and are we assuming that like nuclear power is available, or do we have like a charging stand for those? Curious how we're getting power to the rovers.
Yeah, so there's the whole operation requires a fair amount of power.
Mm-hmm.
So at each crater rim location, there are actually 2 heliostats.
Okay.
One is shining light to the collection dome
Mm-hmm.
to provide the thermal heat for sublimation. The other one is illuminating photovoltaics at a processing facility. And that's providing power for, communications, for the rovers. There's a charging station there. But most of the power is going to the processing of the propellant.
Right.
You get the ice over there. You've got to heat the ice again to get it out of the cold trap, the collection tank, and it has to be purified, has to go through an electrolysis process, and then it has to be liquefied and stored. And so all of those things require power. And so actually most of the energy from the crater rims is going to that process. For the production rates we were aiming for, it was about a 0.5 megawatt required for heating, and then 2 megawatts required for everything else. So total power consumption was 2.5 megawatts. Now, nuclear, you mentioned nuclear. At this stage of the game, we're not obviously settled on any of the concept.
Right.
To me, power is one of those trade studies that still needs to be done in more detail.
Mm-hmm.
The reflected sunlight is very efficient, but it has geographic limitations. As you can imagine, you have to find a location that, has good sunlight at the crater tops, ice at the crater bottom, but the distance is limited. There's a our calculations, you could probably make it work with distances between the heliostats and the ice collection location of maybe 5 kilometers. You could potentially, stretch it maybe up to 10. That's in contrast to power beaming, which is essentially unlimited with line of sight.
Right.
And then, of course, if you have nuclear power at your location, you don't have to have anything up at the crater rims, right? You're all self-contained, and you have nuclear at the bottom. So, nuclear, I think, is a very viable option. And there there are companies out there, and I'll plug one of them, Ultrasafe Nuclear Corp in Seattle is actually working on, space qualified fission reactors that can easily get into the 0.5 megawatt scale. So, providing 5 megawatts, 0.5 megawatt for collection and 2 megawatts for processing. You could just land 5 of those things.
It changes a lot of things. You can have that much power down there.
Yeah. Nuclear is I think a very viable option. And, in my own mind, I kind of, bounce back and forth between microwave power beaming and reflected sunlight and nuclear. And, I think time will tell, as we get, more development for each of those different options and start looking at some of the geographic limitations. I'd actually put a detailed power trade study in the proposal I submitted to NASA recently.
So in the abstract that I had read, you were drilling boreholes and putting conductive rods in there. And I'm curious, is that still kind of, something, have you found that to be more effective than just surface, or have you gone that far yet?
Yeah, so we actually tested that in the test program I mentioned earlier. With our sample was only, say a coffee cup sized sample. But what we did was put a small perforated copper tube, inserted that into the sample, with the heat still being just coming from the surface. It was still just the lamp, but the lamp would also, heat up that conducting rod, and provide a direct path for heat down into the subsurface. But the other thing that it did, which was we found in our testing to be important, is it provided a path for the vapor to escape.
Okay, so that's really interesting.
Yeah. So what we were seeing as you heat the surface, you get the ice out of the surface, and then maybe the first few centimeters, and then you have this desiccated layer, a dry layer of regolith, which number one is it's a very good insulator and then very poor conductor. And so it provides a kind of a cap that prevents heat from getting further down, but it also acts as a vapor barrier. And how much of a vapor barrier it is would depend on, exact grain size and all that kind of stuff of the material. But the conducting rod enabled us to increase the ice extraction rate by about a factor of 3.
Okay.
Which is pretty significant, right?
Yeah.
So, it's one of those things where, in any sort of mining operation, right, you have you spend the least amount of money to get a certain amount of material extracted, right? The analogy I use when I talk to people about this is, the very first gold miners that came to Colorado, they didn't need any equipment beyond a gold pan, right? They were picking nuggets up out of streams.
Yep.
And so that was super cheap, not a lot of capital investment. But once that easy to get gold is removed, then you have to start adding more and more sophistication to the extraction methods. And nowadays, if you go up into the Colorado mountains and, there are gold mines that are still active up in Idaho Springs, for example, they're hard rock mining, with sophisticated machines. And, I look at mining ice on the moon the same way. What's the lowest cost way we can get, the easy to get stuff?
Right.
stuff that's on the surface or in the very near subsurface. And then, okay, what are the, once you've gotten all that, then how do you get the next amount of ice? And so I think it remains to be seen whether these conducting rods need to be added into the initial configuration or not. But, we've proven that there is that option. If surface heating is insufficient, and you can't, make an economic case with just surface heating, then it's a pretty simple add to put in these conducting rods.
So, so speaking of sort of all this, NASA had recently, it was earlier, just a little earlier this year, they put out an RFI about basically if you can obtain regolith on the moon, they would pay you for it. Basically, it was. And my first thought was, why, I was curious why they didn't put kind of like gradated, like they would pay more if you were prospecting, you could get it out of a PSR. It seems that the fact that we've gotten, regolith or lunar rock before from the surface, I'm curious, what your thoughts are on whether or not we could have gone a step farther on asking for regolith from particular spots where it might be more valuable to have a look at.
Yeah, so that's an interesting point that kind of gets into a whole different area, the sort of legal aspects of mining the moon and property rights in space and things like that. So the background, goes back to, the mid 2010s, but 2015, the U.S. Congress passed the Space Commercialization Act, or Commercial Space Launch Act, which had a provision in there that for mining of celestial bodies, space objects. And the important part of that law was that it said that U.S. entities can own materials extracted from space objects. So it established property rights of extracted material in space. And at the time, it was the first ever, U.S. was the first nation to ever do that. Mm-hmm. There was a fair amount of controversy at the time. There was some international furor that, in claims that this violated the Outer Space Treaty that the U.S. is a signatory to. And, the U.S. interpretation is that, no, it doesn't, that it is in concert. In particular, the Outer Space Treaty says that there are no claims of sovereignty are not allowed for celestial bodies. So you can't own the object itself. What the U.S. law says, okay, fine, you can't own the object itself, but you can own what you extract from it, which is very, very important. And that law was actually pushed through by some of those early asteroid mining companies like Planetary Resources and Deep Space Industries, and Moon Express was in there as well. So what NASA recently did was put out an offer to buy regolith. They don't want the regolith, yeah, but what they're trying to demonstrate and set a precedence for is transfer of ownership. So if you own property, then one of the most fundamental property rights there is that I can transfer my ownership to someone else. That's baked into all of our common law. And those were that goes back to John Locke and right, the origins of having property rights of any kind. And so NASA is simply saying that, scoop me up 50 grams, half a kilogram, and then I will buy it from you for a nominal price. And then now that sets a precedence and demonstrates that we have transferred ownership of extracted materials on the moon.
Okay.
That's what it's for. And NASA doesn't want the regolith. It's kind of useless.
Mm-hmm.
I've been actively trying to convince NASA for many years now that they should do what I did in 2016 and, sort of make an open offer to purchase, commodities in space, like propellant, and, help make the market. That's what really needs to happen is we need, ULA offering to buy was, stimulated a lot of interest.
Mm-hmm.
But it wasn't sufficient to actually establish mining companies for space mining. There's some small companies out there, but I think it would be very impactful if NASA would do something like that. Mm-hmm. And, I was happy to see them do what they did with offering to buy, 50 grams of regolith.
Yeah.
But, they're never going to, come collect it. It's
Sure.
just going to sit there.
Sure.
All we had was, a legal title, transfer of title.
And so do you think that gives it quite a bit of power now, or do you think it's going to have to be until that actually happened for the first time before that really kind of?
It was very symbolic, I think. And, I give a lot of kudos to the current administration and NASA for, really pushing hard on the idea of ownership of resources in space. Mm-hmm. They've been very clear in endorsing, the law that was established in 2015, actually signed into law by President Obama at the time, and wanting to take those principles and push them further and, establish those sort of free market principles for space activities. That's in distinction from a lot of people in the international community that want to take the opposite approach, that there is no private property ownership in space, that everything is collectively owned. The view that space is a global commons in the sense that it's, in that sense, it's owned by everybody. But the downside of those, tragedy of the commons, right? That's in our lexicon, that if everybody owns it, nobody owns it. And, it would, in my opinion, really put a damper on any kind of space development if we went that direction. And so I think we're seeing an overt push by the U.S. to go in the opposite direction and get firmly established this notion that you do have private property rights, and we're looking for space to be a free market, not a collective.
Right. Well, I mean, I think that's, all I have today, unless there's anything else that you want to talk about.
Well, on that same point, recent news, within the last month, we've seen, 8 other nations kind of sign on to those principles. Mm-hmm. The Artemis Accords. Mm-hmm. It's not surprising that Luxembourg is one of those countries, because in 2016, Luxembourg passed laws that echoed what the U.S. did in 2015, which established for Luxembourg entities that, the right to own things extracted in space. But now with the Artemis Accords, we have 8 other countries, Luxembourg, and I'll probably forget some, Canada was in there, United Arab Emirates, Japan, Australia. So I've named 5. There are 3 others that I'm forgetting right now. But we're starting to build this sort of coalition, around the idea of free market and property rights in space and cooperation. I mean, there's a lot more to the Artemis Accords than just space resources, but space resources is one of the, core principles of the Artemis Accords. So, we're seeing progress in that, and that's a necessary step to be able to, have companies invest with confidence.
Mm-hmm.
If you're a company and you're going to invest your own money in a mining operation, you want to make sure that, that you're legally entitled to do that.
Right. Right.
And that somebody's not going to come along and nationalize you. And
that's right. Take away the resources you capitalize because it's really expensive to do.
Right.
Yeah.
Right. So those are important developments, and I give kudos to NASA for doing that. And longtime friend of mine, Mike Gold, has been the force inside NASA that's pushed that through.
That's awesome. Yeah, I mean that's really interesting. I hadn't studied the Artemis Accords very very closely, but it looks like I need to. So.
You should take a look at it. It's it's more symbolic than substantive now, but it's taking important steps in the right direction.
That's excellent. But yeah, I mean that's so. That's all I have today. I mean, I'd love, if possible, for to bring you back on when I have when new things happen. You're one of the people that really knows what's going on in this sector, and I'd love to keep talking to you about it.
No, I'd be happy to. It's one of my goals is to promote this field as widely as we can.
Thank you for listening to the Friends of Space Resources podcast, and welcome. Connect with us on social media by searching the Friends of Space Resources podcast, and join us online at friendsofisru.com. Check back weekly for new episodes and new insights into space resources. Until next time, look up and keep dreaming.